Okay, it's time to start the session. AI is ready for you. Are you ready for AI? By rejasupotaro さん。じゃあ、よろしくお願いします。温かい拍手で。Please give him a kindly applause.
Okay, so thank you for coming. This talk is about machine learning on mobile, especially focusing on TensorFlow and the computation graph. I think this is a minor topic, so make sure that you are in the right room. I will try to explain as clear as possible, so that you can follow me, even if you are not, you don't have experience of machine learning. Before getting started, let me introduce myself a little. I'm Kentaro. I started Android development in 2010, and my work was changed a few times, and now I'm in discovery team at Cookpad UK. Well, it's me and my colleagues. Discovery team is responsible for providing users with right content at the right time. For example, search and recommendation are the features we are responsible for. We are always looking for better approaches and technologies to make our product better. Information retrieval is one of the fields which has been evolved a lot in the last few years, thanks to deep learning. And some people are cynical about buzzwords like AI, blockchain, IoT, VR. But look, these are desktops in 2017. They have already productionized machine learning. It's already been happening in our daily life, not only in academia. And I just saw an article that the Google flights will now predict airline delays before the airlines do. So, for example, when I look for my return flight, Google tells that this flight can be delayed. So I can avoid such flights before it happens. So in the future, it can happen. One day, when I send a resume to a company, AI predicts my future performance, then they reject my application without having an interview. And another day, when I attempt to buy an insurance, AI detects the risk of my future illness, then they reject my application. Oh gosh, then in another day, when I pass in front of our surveillance camera, AI detects that I will commit a crime in the future, then I'm arrested. So yeah, this is the future, you know. So this talk is for people who are just interested in AI, and for people who have already investigated the feasibility and wondering how to release to production. Great. Yeah, this talk focuses on what's happening inside. After this talk, you will be able to release your app with confidence, hopefully. I think ML development is still challenging, unlike API development. You understand how to use this API by just looking at this line. What is the HTTP method and what is the path and the parameters. And you can debug network layer using shells or whatever while looking at the HTTP status codes and the headers. On the other hand, ML development has just started. There is no best practices yet. Both machine learning researchers and product developers like me don't know how to productionize research. Machine learning researchers need to know the real environment, and the product developers need to learn machine learning. This is the current status. I feel it's like Android development around 2012, and I feel we need to share knowledge. This is my motivation for this talk. So this talk is based on this example app, and the source code is available on GitHub. We will see how to train, how to optimize, how to deploy through this example app. And there are many libraries such as PyTorch, CaFeTool, Cyano, Chainer, and why we use TensorFlow. The reason is simple. We all love the official way. It means there are a lot of documentations and contributors. Hence, we would love to use TensorFlow for Android and Core ML for iOS. At least TensorFlow is a recommended library to build neural networks in CookPad. By the way, some runtimes support multiple formats, and the graph intermediate representation is actively developed. It converts a specific format to another. In the future, which library we use wouldn't be a matter. If you want to know more about TensorFlow itself, there is a good read published by Google. And if I explain what TensorFlow is in my words, it's a toolkit to build a computation graph, creating and connecting different blocks like Lego. TensorFlow can be used not only for machine learning. We can use it as a calculator. When I run this computation graph, which consists of two constants, this computation graph outputs 5. Most of libraries are designed for research, but TensorFlow is designed for production for various environments, including mobile. So far, it's not practical to run other machine learning libraries on Android, as far as I know. Let's take a look at the architecture. The core is written in C++. Client access to the core through FFI, foreign function interface. TensorFlow provides libraries for mobile devices, TensorFlow Mobile and the TensorFlow Lite. TensorFlow Mobile access to the core through Java client, and they found that they need a platform specialized for mobile. That's why they built TensorFlow Lite, although TensorFlow Mobile already exists. TensorFlow Lite is based on Android Neural Networks API. Vendors customized hardware accelerated layer. The ARM support for Android NN API was announced, and they said it gives more than 4 times performance boost. Anyway, as long as we use TensorFlow Lite, developers don't have to care about the hardware layer. We can first without doing anything on our side. And also, we can see the strong benefit of TensorFlow Lite in terms of binary size as well. As we can see, the size of TensorFlow Lite is much smaller than TensorFlow Mobile. And the TensorFlow Mobile consists of TensorFlow Java and some files for Android. TensorFlow Lite is a minimum implementation specialized for mobile and embedded devices. TensorFlow Lite is still version 0.1.1, and it's available in Android 8.1 or higher. It looks promising. This is from yesterday's session. And Jelly said Google will make Android the best platform for machine learning. TensorFlow Lite will become much faster and smaller and better in the future. We will become to run all machine learning models on apps naturally in the future. So let's see how to run a trained model on Android. There are only a few steps. First, as the library, put the model in the asset directory, run the computation graph. That's it. You don't have to write C++ and you don't have to use CMake. Now your app can predict the result from the input. Now let's see the detail of this simple model. The model outputs values following this rule. If we plot the data, the output looks linear separatable. A simple model will be enough. So let's define a graph. First, define placeholders and the variables. Variables are initialized with 0. Then compute the predicted value, and compute the diff between the predicted value and the expected value. Finally, update the variables to minimize the loss. Simple enough. What we did here is defining a problem, building the computation graph, and finding the appropriate values by iterating training steps. This process is called training. The visualized graph is here. The input is here, x, and the predicted value is here. Then calculate the loss and update variables. Then repeat this process again and again until the loss becomes small enough. That's it. You've already understood how to build a model. The example model looks simple, but once you understand how to build this simple model, you can build your own model by just modifying the graph a little. So you don't need to hard code logic, and the machine learns how to do it instead of you. I mean, hard coding logic is just like this. List all the possible cases. On the other hand, if you trust machines, just give input and the output, and the machine learns what value to return. So now you can build on XOR gate, and also you can build a model which estimate weight using some features like height and genders. And you can build an own language translation model and image classification model. All models work with the same mechanism. In this case, the input is an image. Images can be converted to int array of pixels, and the output is cat or letter. It's 0 or 1. It's the same as logic gate. So we understand how it works. Let's think about release, how to optimize and how to deploy. Practically, we don't learn such a graph in production because there are unnecessary nodes here, and while influence, we don't update variables. Training is a process to find the appropriate values, but while influence, what we need is the predicted value. We use the same graph, but what we want to do is slightly different. So why we need to transform graph? The reason is to enable the model to run on mobile, because supported operations are different depending on the client. And for better performance, computer resources are restricted, and we shouldn't drain users' phone badly. About the implementation, the Python client covers almost features of TensorFlow, but Java client supports a few features. For example, we can't train models using Java client. What we can do is just running a computation graph. If we build a model in Python, we need to make sure that the unsupported operations are not contained for the target client. Otherwise, it causes an error at runtime. We need to strip unnecessary nodes and elements. About performance, we should be aware that the developers are using rich devices. I'm using Pixel 2 XL, which was 800 pounds. But the most used phone on ClickPad is Oppo A37F. There is a big gap between developers and the users. So next, this is the overview of graph transformation. TensorFlow have two files for training: graph definition file and the checkpoint file. Graph definition file is a serialized computation graph via plot buff. It represents how the graph is constructed. checkpoint file holds variables which are updated during training. After a few optimizations, the model becomes appropriate format for each target platform. TensorFlow can output the graph in human-readable format. This is the graph definition of the AND gate. There is a placeholder named x, and there is a variable named bias. Currently, this node doesn't have a fixed value. It is stored in checkpoint file. Let's please and see what happened by this command. Now, these two files are converted, and we can see that the bias became constant, and the node has fixed float value. And the computation graph becomes like this. Now the graph contains only two matrix operations. What we need is trained values. We can split other things once we get it. Next, let's see how graph structure affects the computation cost and the model size. By the way, image classification is a classic task in computer vision. It was known as a difficult and computationally expensive task. Researchers have been working on this task a long time, and there are many pre-trained models like Inception, MobileNet, AlexNet, and these models, there are models for image classification, but the structure is different. And also Cookpad, we have several models for food image recognition. Retrained Inception basically, and retrained MobileNet, and the PatchNet, which is a modified Inception version 3. They are built for slightly different purposes. For example, PatchNet detects areas which are likely to contain food. So comparing these models wouldn't make sense, but anyway, let's see. First, I tried to learn models on Android. We can see the difference. MobileNet is much faster than PatchNet. And also, MobileNet is much smaller than others. I wondered what the key factor is. I used Android profiler, and I found nothing actually. That's because the result depends on the device spec. So instead, I paid attention to the graph structure. I saw it implies the computation cost and the model size. There are visualized graphs of Inception version 3 and the MobileNet and the FoodNet. I benchmarked using a benchmark tool against these models, and the result is here. I found that the number of nodes of MobileNet is small. The execution time is increased exponentially when the number is increased. Of course, operations and the types of node affect performance, but roughly speaking, the smaller, the faster. It's so obvious, though. Good to measure so that we compare. And the transformation tool has many options. I don't explain options this time, but I would say quantized weights option contribute to reduce the model size a lot without sacrificing accuracy. Let me mention about accuracy. Basically, accuracy should be the same if we run the same computation graph with the same input. But as we saw, we need to transform graphs, and it could change the behavior a little. And the data preprocessing affects accuracy too. we modify inputs before giving to the graph to make it work. Otherwise, one particular feature has a broad range of values governs the result. And when we normalize numbers, there are some methods to normalize input. We need to ask machine learning engineers how inputs are normalized, or read Python code by ourselves. And we need to convert images to an acceptable format for neural networks. It was my blind spot that there are some color spaces. Make sure that the same color space is used between training and inference. Otherwise, we can't get the same result, and we would spend a lot of time to find the codes. Actually, I spent, after transforming a model, the size became a few megabytes. I think it's small enough in most cases, but if you don't want to put the model in the app, we can download the model from network. It's not a hassle, just give a file to the interface. There are pros and cons, so it's up to the requirement. If you worry about the library size, we can split the app by CPU architecture as well. And if we apply both, the app is now much smaller. You get the power of machine learning by adding extra 300 kilobytes. Okay, yeah, let me summarize this talk. We saw how to train a model and the difference between TensorFlow Mobile and the Lite, and how to transform a graph, and how to implement client side. If you worry about the app side, there are options to reduce the app side, and also splitting APK as an option. Yeah, that's pretty much for me. Thank you for listening.
Thank you very much for the